receive any email notification regarding class cancellation on Friday from Dean's office? So it's a capstone open house. Usually get an notification, but we'll find out more. So if not, then we'll have one class on Friday and the last class on Monday. Monday, last 50 minutes I'll be giving just the review for the final. That's all. As for the assignment,
These are posted on Canvas.
as for the computer assignment, you will see the due date I put the last day of class, which is Tuesday. Official last day of classes, which is Tuesday, not tomorrow, week after. That's the latest I can give. I cannot give any more extension. And whatever I will cover, I will prepare one homework, couple of homework problems. And I will be posting that today. So if you click here, you see that this time I put a link because I plan on all the theory and all the steps are there. I just plan on putting one box around it, just so you can see. And I also gave you a sample code actually. Sample code where you can just use this template to get started, and then your implementation code will go right here for sample code. And so what you want to do, please go ahead and read this assignment, computer assignment. If you have any question, we'll discuss it in our next class. Because today I just posted this as a computer assignment. So I would like you to go over the assignment that way. You will know what I'm talking about. Otherwise, I could talk about this assignment, but if you read it once, then it is better for me to explain, and you will know what I'm talking about. So only thing I can say is we can decide on the stock. So this year I actually, what you do, the most volatile stock that I got that I found is this one. So you go to finance. Most volatile stock, I don't know all the stocks, I don't know which one, but to me I found Vivian. This symbol seems very fluctuating, and we get no, it's going down. It started here. I want to say something. Can you tell me one symbol, guys? Which one you could think of? That is very fluctuating at the same time it is increasing as well. TBT. QUBT, right? What is this? Okay. So let's see the date. Oh no, it's flat. We don't want to go with this one. Okay, give me another one. How about QCOM? Okay, yeah, this is. Yeah. Okay. Let's go with this one, ECE. So what you need to do, you need to collect data, 5 years. I go by 5 years data. So you collect historical data, and then so you go with, you collect data, 3 sets of data. One is open, high, high, low, and close. These 3 columns, okay? And when you extract data, you can, no, it's not free anymore. You can, if you download, it's not going to give you anything. So one way I did that is, you just select like that, okay? You see, you just select data like that, and then you select 5 years data, and then you open Excel. You open Excel. Okay. You paste it right here. Right click, copy. Okay, there you go. So you paste data here and keep only, this is open, this is high, low, and close. These 3 columns of data. These 3 columns of data. You can just discard the other data, and then what you need to pay attention, what you need to do is you need to pre-process this data. See this row, you will have error when you compute, when you predict stock. You will have error when you, because this row doesn't have any data. You can just delete this row, and also here, every 4 months there is a dividend rate. So you can delete this part, this row. That way you will be able to compute mu and sigma properly. Also this row. Yeah, that's all. So I just focus on 5 years data. So I did mention here. So what I'm going to do, I am going to update this computer assignment, and this time I'm going to update this computer assignment. Here I'm going to replace this star with QCOM. That's what we are going to do. Okay, so you collect daily closing price of the stock over past 5 years, and plot number 1, plot stock price versus time, where time t in days. Okay, and then simulate 100 realizations of. We talked about realization in our last class. What is realization? So you need to simulate 100 realizations of this winner process over 5 years with daily steps. With daily steps. N equals 5 times 252. There are 252 trading days to come. We assume that there are in 1 year there are 252 trading days. So we are considering 5 years of data, so therefore, so n equals 5 times 252 days. And then you will need to generate corresponding stock price for geometric Brownian motion, GMB. So I did not go through this yet. Today I'm going to go through this. So generate corresponding stock parts for geometric using geometric Brownian motion with S naught, which is the initial price, average return per year, and then volatility per year, sigma. So mu and sigma. And then you plot 10 sample paths with semi-transparent lines. And then compute and plot the mean path with plus minus 1 standard deviation in envelope. So which means that you have that confidence interval. I just defined it with plus minus 1 standard deviation. And then calculate the covariance matrix at S2.5 and S5. Okay. So please read it, and this is the code to start with. Please read this computer assignment. I have corresponding background information, and this background note I actually copied from the note that I have posted, so that it is quite self-contained. So this is it's not hard. It's quite simple. This is the last week, and I did not make it make you to generate. I did not write many parts of this computer assignment because it generates many plots. So we have only 6 parts. So please read it before coming to the next class. That way I will be able to give you more hints. Okay? So this year we decided that you are going to work with Q-computer. I will update this computer. All right. Now let's move on to the theory. So, Brownian motion, winner process. Let's go through what it is. It's a random process. Brownian motion, it's a random process. But what I have, even though I will go through some history, and this history I have written it in the document. In this document, and this document I have posted it in the post website. So if you go to Canvas, ECE 302, and you see this PDF file, and this is the file that I have opened. Okay, so everything is there. What I'll be talking about, everything is there. So here, so that you know, because down the line I plan on writing an introductory book on probability statistics and random processes. So that's why I started typing this. So what I did here, central limit theorem from chapter number 7. So I summarized my notes here, and then we went through all of this. In our class. And confidence interval of Gaussian random variable from chapter number 8. We went through this, and in our last class we went through this resistance measurement example. So that I put it here. So yeah, as you can see that in our last class, estimating resistance from noisy measurement, we did that in our last class. And this solution I put it right here. Now today we are going to go through the stochastic process and notate all the notations. I went through all of these notations in our last class. So we'll directly dive into this part, which is Brownian motion. Winner process came later, so it started from Brownian motion actually. Winner process is basically the mathematical version of Brownian motion. And Robert Brown is a Scottish scientist. He's a botanist actually. What he did, he noticed some random movement of pollen grain, which is suspended in a fruit. So what I did, I actually started teaching this topic since last year, and I have been doing research, and usually there are some YouTube videos and some online documentation and some textbook I did. Now, all the videos that I saw, the best explanation I found, you know what, is Wikipedia. That is the best explanation that I found. So if you go to, if you just simply write Brownian motion, here you will see in Wikipedia, this is you see a lot of particles, and you see the motion of pollen grain is called the Brownian motion. See, it's random part. You have no idea about its trajectory. You simply do not have any idea about its trajectory. Just like stock market, you simply do not have any idea what's going to happen. Okay, so that's why we start with this Brownian motion. So he's a Scottish scientist, and he was experimenting. He actually put some pollen grain, and then pollen grain he was trying to see the motion of pollen grain suspended in water, and then this motion has some mathematical. This motion has some mathematical insight, and that mathematics is being modeled by another scientist, American scientist called Winner. So what we have here, this Brownian motion in 1827, Scottish botanist Robert Brown, he actually noticed this motion, and then this motion has been mathematically described by Winner. So it is named after scientist Winner, and we call it Winner process. And scientist Winner, he actually came up with the mathematical description of this WT. It's again, W is coming from this scientist Winner. So this W, and I'm coming to this equation later, but it actually started from this standard Brownian motion. And standard Brownian motion is basically Winner process. Guys, if you recall, if we have a Gaussian random variable, x, that follows Gaussian distribution with parameter mu and variance sigma squared. Guys, look, see the relation. Here, when mu equals 0, and variance equals 1. When mu equals 0, variance equals 1, we call it standard Gaussian, standard Gaussian random variable. Standard Gaussian random variable. So we call this standard Gaussian random variable. Now, the motion of pollen suspended in water is actually modeled using a standard Brownian motion. And standard Brownian motion is basically the Wiener process. So Wiener process, also known as the standard Brownian motion, is modeled by Wiener process. Wiener process has two parameters, 0 and 1. This 0, when we have two parameters, this 0 is basically parameter mu, and this is basically sigma. This is sigma, standard deviation. This sigma is basically here in a random process. This sigma is called the volatility. Volatility. When we generalize this Wiener process, that becomes a Brownian motion. So this is basically generalized Brownian motion. Generalized Brownian motion with parameter mu and sigma. When mu equals 0, sigma equals 1, that becomes a Wiener process, also called standard Brownian motion. Please don't get confused. So that's why I try to relate it to the Gaussian random variable and standard Gaussian random variable. When mu equals 0, variance equals 1, or sigma equals 1, then it becomes the Wiener process, also called standard Brownian motion. When we have generalized mu and generalized sigma, we call this Brownian motion. Wiener process, usually, when you write Wiener process, you denote it using curly bracket, and then this is Wiener WT and comma t greater than or equal to. So this is the standard Wiener process. Now it has to follow certain properties. Real world stochastic process that satisfies the following properties. Number 1, the initial condition is 0. The standard Brownian motion or Wiener process has initial condition 0. So I'm going to draw the Wiener process. So if this is t, time t, you have no idea it's this signal, you simply have no idea what's going on here. But what you do know, that it has to start from 0. So if this is t and we have Wiener process is right here, it has to start from w at time 0 equals 0. Okay? So here it becomes, I don't know, negative something. Negative a, for example, and this is 0. So on what you know, Wiener process has the initial condition w0 equals 0. After that, you have this non-overlapping time interval. Non-overlapping time interval 0, t0, t1, dotted, dotted, t sub n. So what it means, that you divide this x-axis, you call it t0, you call this one t, I'm going to use different color. So this is t0, this is t1, this is t2, and this is t3, and so on. So this interval, these are non-overlapping interval. Non-overlapping interval. These are non-overlapping interval. Now the way you interpret this is the following. So once you have this non-overlapping interval, this condition is very important, guys. 0 less than or equals t naught, t1 less than, strictly less than, all the way to tn. So there will be non-overlapping intervals, t1 minus t naught, t2 minus t1. Now the main point here for this second property, main point here, that this is a random variable, this is a random variable, this is also a random variable, this difference random variable, and all these random variables, these are statistically independent. Statistically independent. These are statistically independent. What it means that the random variable, so let's say this is W1 bar, this is W2 bar, this difference. So W1 bar and W2 bar, the correlation coefficient of W1 bar and W2 bar is going to be 0, and the covariance of W1 bar, W2 bar is going to be 0. So this is an important property that you have, and it is actually coming from this motion. This motion at every non-overlapping time interval. You see this motion, one motion from another set of motion. Those are completely independent, completely statistically independent. You have absolutely no idea what's going on here, the motion. You simply cannot predict. And if we assume this certain property, Wiener process, if we assume certain property, then in chapter 10, we are going to use Kalman filter to actually estimate this prediction. Once we assume certain properties, this Wiener process property, once we assume these properties, then we will be able to somehow estimate this motion. You will be predicting the stock market Qualcomm. You will be predicting like after 5 years. You have 5 years data, and then from, like, let's say today is April 27th. So you collect data for the last 5 years, and then you are going to predict stock, that Qualcomm stock, for next 5 years based on the two parameters, mu and sigma. Now, this prediction, you will see this prediction as you go, this prediction will be uncertain. And mu and the sigma parameter sigma is going to be higher and higher. But how you can actually how you can filter out some noise and make accurate prediction. So that prediction is going to come once you assume this property. Therefore, this property is very important, statistically independent. So this difference, WT1 minus WT0, WT2 minus WT1, these differences are statistically independent. So you can think of these as a random variable, and these random variables are statistically independent. Next property we have is Gaussian increment. Now we simply cannot skip, or we simply cannot forget the Gaussian random variable, properties of Gaussian random variables. So now we have these increments, Wt minus Ws, so which is basically W at time t, W at time t, and W at time s, W at time s. Now t minus s will be non-zero. So therefore you will have this time interval. Now what is the difference between Wt and Ws? This difference has to follow Gaussian random variable with parameter 0, which is mu equals 0, and this t minus s, this time increment t minus s, is basically sigma squared, which is the variance. T minus S is the variance. So this increment has to follow Gaussian distribution. Again, please make sure you know the notation. This N is the normal distribution or Gaussian distribution with two parameters, 0 and T minus S. And the mean of increment is 0 and its variance sigma squared equals T minus S, which is the length of the interval. So here, this difference I denoted with W bar. This difference I denoted with W bar, and I showed you graphically what this difference is. So this is another property. Now, stationary increment. The distribution of Wt minus Ws depends, this difference depends only on the time difference T minus S, not on the actual value of T and S. So you simply don't pay attention to T or S, only take the difference, and this difference, you take this difference, and this distribution depends only on this difference. And what does that mean, stationary increment? Which means that this difference is going to be a random variable, W bar, this difference is a random variable. And then you will have stationary increment, which means that Wt minus S at this point, and Wt minus S at this point, Now what does that mean, stationary increment? Wt minus S, which means that we have W bar. The mean and variance at this point is exactly the same as the mean and variance value. That's why that's what it's called statistically independent, as well as it's called stationary increment. So the increment will follow this Gaussian distribution, and you will have the same mean and variance, as you can see. This difference 0, and you have T minus S. This difference will have stationary, because it's a random variable, and this random variable will have stationary increment. Continuous path. With probability 1, you will see the function Wt or T maps to, so this symbol is called maps to. T maps to, so there is a notation here. This is a vertical part here, and then arrow, T maps to Wt is continuous for all T greater than or equal to. Although it is nowhere differentiable means, again, it's so unpredictable, it's so random that at any point you have no clue. You simply cannot take the derivative here. At no point it is differentiable. But this property that we are going to ask, this property says with probability 1, the function Wt is continuous for all T greater than 0, although it is nowhere differentiable. So it's continuous path. At the same time, we are claiming that it is nowhere differentiable. Now we come to another definition here. Expectation of Ws and Wt. So we have two random variables at two different time instants, and this expectation becomes correlation. Actually I wrote it right here. The correlation is going to be minimum of S and T. Now, this winner process is very useful with parameter, like generalized winner process with parameter mu and sigma, which is generalized, which is basically Brownian motion. Brownian motion with parameter mu and sigma. Now, some applications of winner process includes modeling thermal noise, stochastic modeling of stock prices, which we are going to go through. And then signal modeling, filtering and control theory, a derivation of, actually this part is my part, filtering and control theory, and I'm going to explain one of these in the second topic of Brownian motion. So this is actually my part, and this part actually I studied and started learning since last week, which is derivation of stochastic differential equation. So now we come to the stochastic differential equation. You guys learned in mathematics, in any of the courses, any of the DPQ courses, you did not actually heard about this SDE. So you did hear about ODE, right, guys? ODE, what does that mean? Ordinary differential equation, right? ODE, you did hear about ODE, but not the one that I'm going through. So this, again, in our last class I did mention that financial engineering, they actually start from this stochastic differential equation. So they have this background on ordinary differential equation. This ordinary differential equation, how does it work? Ordinary differential equation, so let's say dxt over dt equals axt plus b ut. So this is OD, ordinary differential equation. Okay? So you take the derivative of x with respect to time, and you have the state variable x, and you have the input variable u. So you can actually somehow find what is xt, which is the solution of ordinary differential equation. So now, guys, try to relate what I'm talking about. Is this stochastic differential equation. So I'm going back again to my ordinary differential equation. If I have dxt, guys, we have dxt equals a xt dt plus b ut dt. Look, here we have this dt, term dt right here, and here we have dxt. Now the difference in stochastic differential equation is that you have dst, that's okay, but here you have dt, here you have another term which is dwt. And this differential equation, who came up with this differential equation? Japanese scientist, his name is Ito. Ito is, you can Google Ito differential equation. Yeah, Ito differential equation. And there is whole calculus on it. So you can see you have two different, you have dbs, as you can see, you have dbs and ds, and if you take the derivative, if you take the time derivative, it becomes Ito differential equation. And so there are entire calculus is right here. So we'll directly move on to Ito differential equation and solve it. So now we go here. So this is basically Ito differential equation. It is named after Japanese scientist Ito. And this equation is used for stock price modeling. Now, here ST, I intentionally put S just because we are dealing with stock price, okay? So stock price is a stochastic process, so S denotes the stock price at time t. And mu, in general, it is called drift coefficient. In general, mu is called drift coefficient, but mu, I did mention in the computer assignment and in the sample code as well. This mu is basically the average return. Average return. Okay. This mu is the average, mu times st dt plus sigma times st, and this is basically the difference in winner process, d wt, and wt is basically the winner process. So it is a stochastic process with all the properties that we went through. Now using E2 calculus, using E2 calculus, you can go through like all these, Wikipedia, all these complex mathematical description. You can use E2 calculus, and then using E2 calculus, I did not go through all the derivation here, it's going to be too much math. So if you apply this E2 calculus and use bunch of logarithm properties, you will end up with solution of this stochastic differential equation. So stochastic differential equation, it is basically came up with scientist E2, so people also call it E2 differential equation. And then you will, if you apply E2 calculus, you will end up with this equation. And this is basically the solution of E2 differential equation. This is solution of E2 differential equation. And this is the equation that you will use for your stock price. Okay, for next 5 years. Stock price modeling for next 5 years, this is the equation that you will use. So you start with today's stock price. You start with today's stock price, and for in next 5 years, using average return for the previous 5 years and using volatility in the previous 5 years, mu and sigma, you use this equation to predict stock price for next 5 years. So S naught is the initial stock price. This shows that stock price follows log normal distribution, and its randomness is entirely governed by the properties of winner process. Now, how to implement it? Yeah, there are a lot of theory behind it. I just summarized, like after studying many articles, watching many videos, and entire chapter. So I actually summarized how we implement. So I actually learned things by doing. So I did implement this equation. That way, I see what I'm doing. So what you do, estimating mu and sigma from historical closing price. Okay, let's explain this after taking five minutes break. Okay, so let's explain this part because this part you need to understand so that you know exactly what.